So the last couple of weeks have been doing about particle accelerators, and why do we need particle accelerators? Because particle accelerators have allowed us to work out what matter is really made of. So looking this week in terms of particle physics, and it's what we call the standard model of matter. And this is the content statements. As you can see, there's a whole heap of new words. I've highlighted every one of these new words, which you probably haven't heard much of at all before. And so although there's not a lot of calculations in what you're going to be doing, there's certainly a lot of new vocabulary. It's going to be more like a modern languages class. So our existing model of the atom, introduced by Niels Bohr, you've got a positive nucleus with protons and neutrons surrounded by electrons which are orbiting in mostly empty space. Oh, so far so good. These electrons can be promoted up or down to different energy levels as they move between different orbits, as you'll find out later on. Well, we've actually got two sets of fundamental particles, those which actually make up the stuff which we experience all around us, in other words make up mass or matter. They're the fermions. And there are also particles which allow us to have forces between things, and they're called the bosons. So we'll come back to bosons later on. Firstly, the fermions. There's two types of fermions, there's baryons and leptons, and they're split into these two types where baryons are made up of other things, quarks, and that includes protons and neutrons. There's also another 4 types of baryons as well. There's also the leptons, when they can't be split up at all. So for instance, electrons are a lepton. Protons, neutrons, and electrons are the 3 things that actually make up our everyday matter. All the others are actually much more exotic particles. So, just to recap, that stuff, that's a block of brick, and it's made of atoms. The atoms are made of electrons in a nucleus. The nucleus is made of protons and neutrons, and the neutrons and protons are made of quarks. So that all subdivides where fermions are the matter particles. There are leptons which include the electron, but there are actually another 5 if you include the neutrinos of those there. All these other ones, one of the reasons you haven't heard about them is they only exist in particle accelerator experiments or in astronomical events like supernovae or the start of the universe, you know, that kind of thing. The hadrons over here, you've got the 2 types. You've got the baryons, which have 3 quarks, and that includes protons and neutrons, and then mesons, which have a quark and an antiquark pair, given that matter can have antimatter, as you will find out later on. There's 6 types of quarks, but the 2 which actually make up most of the things that you experience are just the up and the down quark. There's also top, bottom, charm, and strange, and at this point, yes, you're thinking that physics is just making up these names as they go along. So we've got 6 different leptons with a charge of -1 electron charge or 0 charge. The electron's the most obvious one, and that's responsible for most of our electrical and chemical reactions. It's also got its own electron neutrino, which rarely interacts there. Then you start to get much heavier or much more difficult to obtain muons and taus, both with their own neutrino. So they're all leptons, and they're not made of anything else apart from just what they are. Over on this side, these are the quarks. So you've got up and down quarks, and that's what makes up neutrons and protons. You've also got charm, top, strange, and bottom. They're heavier, and again, much more exotic and much more difficult to come by. This is the way they're all set out, and you'll be doing a diagram of this and also sorting out why they are in this particular order, why they go that way, and why they go that way in terms of this grid. And this is the standard model of elementary particles. And it's a shame that you haven't heard about it before, because it's been described as one of the most successful discoveries in the whole of physics. So I'm going to pause that there now. We'll come back to bosons later on, but there's some things I'd like you to do with the elementary fundamental particles first off.